Okay, so we're continuing 14.8, the very last section of our chapter, and we're using Lagrange multipliers. We're going to have one more lesson after this one, though, but really just a review of what we have done the other day. You can see that you're given a constraint. You're given a function, and usually when you see this level curve, like g of x is equal to a constant. It's a constraint. Your g of x in this problem is going to be x squared plus y squared plus z squared. That, of course, is the equation of a sphere, as we just read earlier. So we want the points on that sphere where another function, f, has its maximum and minimum values. Now, Lagrange multipliers will say that the gradient of f is going to be a scalar multiple of the gradient of g. And really we're using lambda as that constant. So let's find the gradient of f very quickly. The derivative with respect to x with this f function would be just 1. Wow, you can just come up with a constant. How about the derivative with respect to y? -1. And how about the derivative with respect to z? Just a 1. Wow, a little surprising perhaps. And then we'll take a look at the gradient of g. And of course, g is just this function right here as we've written up at the top. This is looking a little bit different. That would be partial derivative with respect to x, a 2x. Partial derivative with respect to y, 2y. Partial derivative with respect to z, 2z. And as we follow the Lagrange multiplier guideline, please do remember we're going to be setting up a system of equations where not only are we saying that the gradient of f is equal to lambda times gradient of g, we also have this other x squared plus y squared plus z squared equals 1. That's the last piece of the puzzle, the last equation in our system of equations. So if we were to just set up lambda, look at your x, components of your vector. We'd have 1 is equal to lambda times 2x. Similarly, we'd have -1 would be lambda times 2y. And then finally, we'd have 1 is equal to lambda times 2z. Then, as I said earlier, don't forget the constraint x squared plus y squared plus z squared equals 1. But I think it's here that perhaps we might get a little uncomfortable. You might think, now, wait just a minute. As we look back to our first example, you might have noticed that very nicely we were able to solve getting x and lambda on one side, factoring out some terms using a zero factor theorem to help us, and we could find values of x and lambda that would arrive at 0. And then our second example, maybe we had to do a little bit of work to make some substitutions for y and for z. Generally, that's what we're going to have to do. We're going to have to solve for one of our missing pieces and then go ahead and make substitutions. I hope you're noticing something. There is a common ground here. In all three of those equations, you're going to see we have a 2 lambda. So I know it's very tempting to solve for lambda itself. I'd actually like to solve this first equation for 2 lambda. You can think, well, why? Well, because that's what I see in my other 2 equations. I'm going to replace 2 lambda with 1 over x. Likewise, over here, I'm going to replace 2 lambda with 1 over x. And then I hope you can see I can very easily solve for y. And I can solve for z. And it's at this point where we can look and say, well, again, we might not have found specific values for x, y, or z. However, I now have something I really can work with. I have my x solved for arbitrarily, just saying whatever x is, but my y would be in terms of x, and so would my z. So let's just leave x as it is. Y squared, well, y is going to be negative x. I'm going to work that out. Z, of course, is just going to be x itself right here. And my word, as I go to that last constraint equation, I can find that really I've got x squared plus x squared plus x squared. And x squared plus x squared plus x squared is 3x squared. Wow. And then I can go ahead and I can divide by 3. And as I take my square roots, guess what x would have to equal? Either the positive 1 over radical 3, taking a square root, or the negative of it. Are we doing okay? Now, at first glance, you'd say, okay, so x is equal to that. Well, guys, please understand that, now I know what y is and I know what z is also. So I can have an x comma y comma z. I could say, hey, look, I'm going to have an x of a positive 1 over radical 3. That's one possibility. The y value would have to be the opposite of that. My z value would be the same thing as my x value. But of course, x could also be the negative 1 over radical 3. In which case, the y would be the opposite, and the z would be identical. So I found my critical points. Now what? I'm going to go back up to my f, which is really x minus y minus z. And I'm going to try to find out what f really is going to equal here. Yes. Oh, is it plus z? Thank you so much. Yeah, we would have had a very funny answer. Thank you. Okay, so from here we can say, well, look at this. We'd have 1 over root 3 minus a negative 1 over root 3 plus a 1 over root 3. Guess what that really becomes? Well, a 3 over root 3, right? Isn't that what we'd get? And then you'd say, well, what if we made these negative? If I had a negative 1 over root 3 minus a 1 over root 3 plus a negative 1 over root 3, what would that be? Negative 3 over root 3. Now at this point, we can name the absolute maximum and the absolute minimum for the function. Guess what our absolute max is? Absolute max of 3 over root 3 at the point 1 over radical 3, negative 1 over radical 3, comma, positive 1 over radical 3. Similarly, we can go ahead and say we've got an absolute min of the negative 3 over radical 3 at that other location. So what did we just do? Well, we found our absolute max and min values. We also found the x comma y comma z where they occur. We doing okay? All right.